So we're going to have a lecture now about the sampling distribution, and this is going to be how we estimate the mean of a random variable. And so let's talk about this problem here, because we're estimating the mean of a random variable x. So we'll be given some random variable x, and it has, this random variable has all of these values, and this capital N might be a huge number. We might not have any way of actually knowing all of these values. Okay, so we might not be able to calculate what mu is directly when we're given the random variable x. Okay, and so we wish to estimate it, and so we take a sample of size n and calculate the mean of this sample and get an x bar. Now, unless you are just horribly lucky, you're not going to know whether this x bar x bar will not be right. This will not be right. There is always error in it, but that error, x bar minus mu, is something that we want to gain control over. Okay, and we're working our way slowly towards that. Okay, now, so to do, in our first step of doing this is to talk about the sample mean. And so we're given a random variable x, and we wish to construct a new random variable from that. So this random variable x bar will depend on a fixed sample size of n. Okay, and n we'll want it to be as big as practical, but we'll talk more about what that size is later. Okay, now our original random variable has its population, whatever its population is. The population of the new random variable is the set of all samples from that original population that have size n. Okay, and so as a consequence, the new random variable has a huge population. Its population is going to be n, choose little n. So big N, choose little n is the new population. It's the size of the new population for x bar. Okay, so now one thing that's very good about this new random variable x bar is that its mean, its average, its expected value, which we denote as mu sub x bar, is exactly the same as the mean of our original random variable. So this is good. If we know the mean of x bar, we will know the mean of x, and vice versa. Okay, now the standard deviation, okay, is also related, and I'm going to give you two ways that it's related. We're only going to use one of them, but I think you need to know the truth. Okay, when we have a standard deviation of x bar, it is equal to, okay, the standard deviation of x divided by the square root of n times the square root of capital N minus little n over capital N minus 1. Okay, now when x is much bigger than, when n is much bigger than little n, we can get away with this much simpler formula, and this is the one we will use most of the time, that the standard deviation of x bar is equal to the standard deviation of x divided by the square root of the sample size n. Okay, now how can we get away with that? Well, let's do a simple calculation. When our population has 1,000 elements in it, and when we take a sample of size 30, this quantity right here, the thing we're multiplying by, is equal to 0.970970, which is pretty close to 1. And the bigger my population size gets with respect to my sample size, the closer that this will be to 1. And so since in statistics we're dealing with quite a bit of error all the time anyway, we really don't lose that much by just simply saying, assuming this is equal to 1, except when capital N is small. Okay, now let's take a remark about the standard deviation of the sample mean. As the sample size gets bigger, the standard deviation, okay, gets smaller. Okay, and so this means that since the mean of x bar is the same as the mean of x, that the values that x bar takes, meaning the individual sample means, will tend to cluster closely around the mean of x. Okay, and this is why x bar is a good estimator of mu. Okay, now one last item, this quantity here, okay, square root of x bar, sigma of x divided by the square root of n is referred to as the standard error of the mean. Okay, that's something will use and you'll need to remember.